new episode of Advent of Code 2016. In fact, it's not even exactly a new episode. Well, it is. I mean, you're watching it, right? But also, it's been a couple weeks, I think. Maybe a little less than a couple weeks, but I'm streaming this one live tonight. So, if you're watching it live, this comes as no surprise to you. And if you're watching it from the archives, you probably don't care too much. But I thought I would mention it. If for no other reason than that it might be in the wrong order in the archives for a while. I've got a few episodes pending that aren't published yet. So, I don't know. I think we have. If you're just watching the YouTube videos, I think we haven't done 18 or 17, and maybe not 16 either. I don't know, but those videos will come up eventually, and then when they do, I'll try to put the playlist back into the right order. So, as always, I've got this little prep time here at the beginning for everyone to show up, settle down, pop some popcorn or whatever. I don't know what you guys are up to when you're watching this stuff, but whatever it is, I hope you enjoy it. And you've got still got a couple minutes. Grab a drink, get something to eat. I don't know, turn on a movie so that you can watch something else. Don't do that. I mean, you can if you want that. That's up to you. Say something in the chat, whatever you like. What type of problem do you think this one will be? Asks Marvin Beck. I don't know. Probably programming. You say breadth first search, but actually I've been using an A-star search algorithm for all of the searches. Has not really helped me that much, but in principle it's substantially faster than breadth first. I was hoping that we would get some search algorithm problems where breadth first is not efficient enough, because then my A-star will be helpful. But that has not really happened yet. They've all been either so large that you needed to do more domain-specific pruning, like problem 11, or so small that breadth first was fine. But nonetheless, I do have an A-star search algorithm lying around. So, Marvin Beck comments, I haven't slept in 24 hours, and I am determined to leaderboard this one. Boy, if you're going to do that while you watch me, more power to you, I suppose. That sounds like a lot of work. I can barely do one copy of this program at a time, let alone listen to someone else talk about doing it a different way. No, I mean, day 11, just a naive A-star search algorithm was fine for the small problem and took an hour for the second problem. So, domain-specific optimizations would have made it much, much faster. Maybe doing it breadth first would have made it even slower than an hour. Probably it did, right? I managed to do day 11 without figuring out any domain-specific pruning. Just remove duplicates, examine the most promising paths first, and it solved in an hour, which was not great, but it was acceptable. So what are we down to? 1 minute 20 left. And we have at least a few people here watching. I never quite know, because, when you look to see who's in the chat, it only tells you people who have talked in the last 5 minutes, which I think is reasonable. It shouldn't, if you want to just watch the thing anonymously, it shouldn't tell me you're here. So I see that there's, allegedly 4 people watching, and only 1 person chatting, which, totally fine. But I never know, how much... traffic is the wrong word. How much... maybe, I don't know. Traffic is fine. How many viewers I am getting to these things live. They certainly seem to pick up a lot more after the stream than during. But I think that the fact that it is being streamed live makes it more exciting, even if you don't watch it live. Hey, Topaz is here. He says, I've talked in the last 5 minutes. Well done. And Pedro Osorio? Yeah, Osorio says hello as well. Sorry I missed your Q&A, Eric. I just was busy doing errands. I hope it went well. There was not a recording, so I didn't watch the recording either. Here we go. Time to get started, and go. Day 19, an elephant named Joseph. The elves contact you over a highly secure emergency channel. Back at the North Pole, the elves are busy misunderstanding white elephant parties, okay? Each elf brings a present. They all sit in a circle. numbered starting with position 1. Then, starting with the first elf, they take turns stealing all the presents from the elf to their left. Okay. An elf with no presents is removed from the circle and does not take turns? So we have 5 elves. They each bring 1 present. Yes? Okay. 1 takes the present from 2. 2 skips, because he's got nothing. 3 takes them all from 4. 4 doesn't. 4 leaves, so now we have just 1, 3, and 5. 5 takes them all from 1. Oh, I see. Okay. I feel like I've seen this problem before. Yeah. You can, I think you can pretty simply, like, if you knew the answer, like, there's just some function you can write that's very simple. But I don't know what the answer is, really. Oh, Topaz says there is a recording. Okay, there wasn't when I looked, but that was only like half an hour after the stream ended. So, by the way, I'm not really planning the leaderboard. You know, if it happened, it would be nice, but we're going to try to just write a clean solution. Okay, so how is the right way to do this? Basically, the fact of how many presents they are taking is not that interesting, at least for part 1. It's just a binary thing of, like, do they have any presents or no presents? So we could sort of model this as a queue, where, like, let's say 1 is in the front of the queue. We pop him off, and then also pop off the guy in front of him, 2, and then put 1... we put 1 back at the end of the queue, right? And then 3 and 4 get popped off, and 3 gets put back to the end. And then 5 and 1 get popped off, and 5 gets put back at the end. Yeah, okay. So this is... we could do that pretty quickly, right? It's a rather large input, but okay, that seems fine. So let's try it. Import queue. Puzzle input equals this number here. And it seems like we can just almost like solve this without writing any functions at all. Q equals Q dot is it just Q? Like, how do you make it? Python new Q. Actually, I should be able to do this from Emacs, right? Help of Q, please. Creates a queue object with a maximum size. Okay. Of puzzle input for I in X range of puzzle input Q dot put add put of I plus 1. So that fills it up. And at the end, 1 will be in front of the line. And so we'll just say while not q.empty. Let's see. Winner equals q.pop. Q.pop again. Oh, actually, while q.size. Is it called size? Empty, full, join, put, queue size. Return the approximate size of the queue. That's not very useful. Let's say get no weight, maybe. Well, all right. While not q.empty, if what happens in the get no weight case? So let's say try q dot. Oh, it's not called pop, is it? It's called get. Get no weight, and we'll just do this. No weight. Loser equals q dot get no weight. Except, how do you do exception handling in Python? Python catch exception. There's like a try and except, but I don't know what the syntax is for like specifying what kinds of exceptions you're catching or what. Try except, and then the name of the exception. Okay. Otherwise, raise the empty. Except empty to be print winner and break. Q dot put of winner, right? That seems okay. Python source.py, like how does that go? It's running. In the meantime, let's see what the chat is up to, shall we? Oh, I see. The recording of Topaz's Q&A only lives on his computer. All right. Well, we're not making a lot of progress this way. Maybe it will finish eventually. I think this is fine. It will finish at some point. Oh, Q instance has Q dot. I typed it wrong. Q dot. How did it only break just now? Oh, we were just adding. Wow, that was just adding stuff to the queue. All right. Well, that's exciting. We could put in some flavorful printing, like here. We could print, winner kills loser or whatever. I suspect that for part 2, we'll need to know like how many presents they each have or something somehow. So we'll need to, but I don't know. I thought it would be nice to try to get on the leaderboard for part 1 since it was such a small problem. Print done loading, just so in case this happens next, in case I have another problem, I'll at least have some information about how much progress we've made. Yeah, so this queuing approach is okay. What would be a better way? Because I feel like the right answer... This is definitely a well-known problem, but I don't remember what it's called. Or, like, what the right search terms would be to find it. And I think it's just, like, some sort of, mathematical expression you can use and, like, get the answer for any given n, where n is the number of things. Basically, we're just removing every other elf from the list and doing that until there's none left. And so there's some weird stuff with modulos and whatever. I don't know. Okay, well, we got a new exception. Empty is not... Gosh, dang it! Oh, man. It said empty. It said it was just going to raise empty. That's what the documentation said, right? Am I crazy? Get no weight. It will raise the empty exception. How am I supposed to catch an arbitrary... All right, can I just do this? Is that legal? Def foo to be try pass except print woo, like raise that. Can I like raise arbitrary things? I don't even know. Yeah, I can. So that works out okay, fine. Okay. So you can just catch anything without saying what you want to catch. So we're going to run this one more time. I guess what we should have done is, and let's do that now, def solve of n that does this. Return winner. And instead of puzzle input, it's n, And down here, we'll just write print solve of puzzle input there. And so now we can do in the REPL like solve of 30 or whatever. And it's elf number 29. Let's try the example. In 5, it should be elf 3. Yeah, okay, so it looks like we have a correct solution now. It took a few tries, and as such, we are probably not making the leaderboard, but it makes me sad, like, I don't know, that you don't run into, like, in Python, using an incorrect name for a thing is something you don't find out at compile time. It makes me sad, right? These two errors that have cost us a minute or two each are things that the compiler could have told us ahead of time, except that the language is attempting to be extremely dynamic and says, well, you know, who knows? Maybe he'll define something called empty in a metaprogramming thing, you know, in some other whatever. All right, so here's an answer. Rank 103. All right, thanks, Python. Rank 103. Oh, well. We don't need points, right? Wow, okay, this is a longer part, too. Realizing the folly of their present exchange rules, the elves agree to instead steal presents from the elf directly across the circle. Well, that's a completely different matter. If there are two elves across, then the one on the left is stolen from. Well, that's a lot more difficult. Okay. We can't just use a queue. So, day 19, part 1. How do we figure out who is across in the queue? We kind of need a list, right, where... So if we had a dynamic array kind of thing where it's cheap to remove a thing from the middle, it would be pretty simple. We would just do that, and then we would like... If we could cheaply access and remove items from arbitrary positions, we could just like start from the current position, add the size of the queue divided by 2, and like there's the answer. Modulo the size of the queue, of course. But we don't exactly have that. What if we like tried to use a map where the key is an int? It's cheap, or a dict, I should say, where the key is an int. It's cheap to take something out of that, but you kind of have to renumber all of the existing ones, or else what's the point, right? We could have a fixed size array and just mark entries as being invalid, but that doesn't really help. Because, yeah, I mean, What if somehow each elf knew the distance between him and the next elf on his left? Then we could remove elves in the middle by just like marking them as empty, or indeed just leave them in there and never visit them. Right? That's an interesting idea. So if we start with each elf knows that I'm elf number 1, and to get to the next elf who's still alive, so to speak, just add 1. And then, but elf 2 says, oh, actually, since we removed this guy here, to get to the next elf who's alive, add 2. And then it seems we could, at any given time, we know how many elves are left. And so we know, do we know the distance of the next elf that we want? Not exactly. I guess the distance to the next elf is not exactly what we want to know, right? It's how many elves we've encountered on the way. So we'd still be iterating through the list a lot, like iterating through a lot of list entries to find it. Topaz says, if it makes you feel any better, there are 100 silver stars and 1 gold star so far. Okay. I'm not too worried about it. So, So we can't really use a queue, right? That's the wrong data structure because we need to be able to take stuff out from the middle. I think the idea has got to be using an array, or a list, I guess, and it's very expensive to actually remove an item from an array, but it's not too bad. Well, geez, you have to do... If we follow this whole distance marking scheme that I was thinking of, then to go from one elf to the next, you have to iterate through half of the remaining elves. At which point, you might as well just, like, do the whole work of creating a new array that's one item smaller and just indexing into it. You're saving yourself half of the work compared to doing that, which is not so great, considering it's a lot more like programming work to save yourself half the compute time. And I feel like there's got to be a solution that saves us a lot more than half of the compute time. Maybe let's think about some invariants that we could keep. I don't know. I'm not sure exactly what I'm going to come up with, but sure, that's a good thing to think about. I'm just really stuck to this idea that I had of like tracking distances, and I'm having trouble getting it out of my head to think about alternative approaches. I kind of want to make it work, even though I don't see how it's going to be that efficient. What are other... Like, if we had something like finger trees, maybe? I don't know. Finger trees are the answer to, like, every weirdo list concatenation and destruction problem, but most languages don't have them, and even in languages that do, they don't actually perform as well as you might think because of cache problems. I mean, we could just do it like the dumbest way possible, but I don't know. I guess I'll code up the dumbest thing possible, which I think is maybe twice as slow as the version with distance tracking, but a lot simpler to write. And then at least have that running while I try to think of something smarter. So let's do that. Let's have def solve 2 of n is elves equals range of 1 to n plus 1. I think. So what is a range of 4 to 8? I'm hoping it's numbers 4 through 8. 4 through, right, 7, of course. Yes, okay, so I want the n plus 1 here. And basically, we're just going to say while elves, while len of elves greater than 1. Oh, it's a little tricky because I have to remember which one we're even thinking of, actually, right? I guess we have to have an I as well. I equals 0. That's a little bit tricksy, but all right, let's try it. I guess we just say elves equals elves of... This is a little bit... I can't even figure out how to remove one cheaply, can I? All right, maybe doing it with a list is not so easy as I thought. Possible to show the code. Good suggestion. Why don't I do that? Thank you for the reminder. I got a little bit caught up in trying to figure out how things are going to work. I was going to try just like remove... Wait, can you... What happens if you call del on an array? Help of del? Like, is that a thing I can do? No, of course not. So let's say I said x's equals range of 4. And I now wrote del x's of 1. What do I get? That actually works. That's quite remarkable. I assume it's very expensive. But okay, we can do that. Del of elves of I plus len of elves over 2. And all of this mod len of elves. I equals I plus 1 mod len of the new len of elves. And then just like print elves. Actually, return elves. Return elves of 0. And let's print solve 2 of puzzle input. Right? So let's try now, before we do that though, solve 2 of... What's the example given here? They give us 5 elves. And the answer is 4. So that's the wrong answer. Okay, good news. So probably something wrong with our modulo stuff. Topaz remarks that yes, del x's of I is very expensive. It is $200 per use. Yeah, okay, fair enough. We are... The problem is we're skipping over some elves if we delete the one that is before us in the sequence, right? So let's actually say his enemy is this. Enemy, and also if I is less than enemy, we'll do this. Otherwise, there's fewer items in the array, and so it should automatically cycle itself, right? And now we get 2 as the answer. All right, so let's try just starting this solution. And in the meantime, think of a better way to solve this dang problem. I don't know of a data structure that has good performance for all the operations that we need to do. Like, I don't really know what skip lists are, and we have a list and we're skipping some things, and so I'm thinking like, hey, maybe a skip list is the answer, but that's just like arbitrary word-based pattern matching, which is not really going to help with solving a real problem. But like the amount of time that we're taking here, I gotta say, it seems like it's gonna be about 3 million times as slow as part 1, like roughly. That's about how slowly this should run, I think. Which makes me a little bit pessimistic as to whether we will finish it this year, let alone tonight. So how can we do better? The number is large enough that running this simulation is a thing that is possible to do, but only if it's cheap to do each step, right? In fact, I think if we were to switch to the distance tracking version that I was talking about, it would probably be even slower, because while in principle the number of operations that need to be done is about half as large, we would be doing them by hand inside of interpreted code, whereas I bet Del is, some pretty well optimized C. So even though it's doing more work than us, it's doing it a lot more efficiently. I think actually it might be a good idea to get an estimate of how long this is going to take by saying if len of elves, say mod 10,000 equals 0, print len of elves, and we can see like how we're doing. It's going to slow us down a bit, but we'll at least have some idea of whether we're making any progress. I suspect that we'll basically never see this print because we won't even get through 10,000 elves in a reasonable amount of time. What if we started out with each elf just sort of knowing who sits across from it? I don't see how that helps. Okay, hang on. So we're doing a ton of unnecessary work in just the first cycle alone, right? Or no, I was thinking that in the very first iteration, elf 1 would eliminate the elf exactly halfway across the circle from him, and elf 2 would get the elf just to the right of that, and elf 3 would get the elf just to the right of that, and we'd sort of just eliminate exactly a semicircle. But that's not true, because the size of the circle is changing, and so So I don't think we can do anything clever like just delete the whole second half of the elves. All right, well, the number is going down. If we're willing to wait about 150 times as long as we have waited so far, we'll probably get an answer. So I mean, that's an upper bound on how long we're going to be sitting here, but it's a pretty long upper bound. It also might be the wrong answer. Oh, wouldn't that be bad? Can can we do anything clever? Like, so the puzzle, as stated, has told us about these presents that are being taken, right? And the solution, so you could say, well, that's just flavor, and maybe it is, but maybe it's hinting at us that tracking the number of presents that an elf has can help us somehow. And interestingly, the number of presents that an elf has is the distance between it and the next elf to its left. The thing I was thinking of tracking is how many presents that elf has. Yeah, because they all start with 1, and there's a distance of 1 to get to the elf on their left, then you take 1, and then there's a distance of 2. And if that elf had taken any, then the distance would be higher. So that is actually pretty interesting. It sounds kind of like a clue from Topaz that that's a good way to solve the problem. Even though right now, to me, it seems like it would be, at best, twice as efficient as doing it this way. Oh, wait. No, it's actually super cheap to compute how many elves, what the distance from you to the next, your leftmost elf. You just count the number of presents they had, and you add it to your current number. Okay. Yeah, we can do that. So we'll make a new approach where we store at each offset of the array a tuple, which is the elf's number, which we need in case they win. And actually, we don't even need that. We could use the index in the array. But, yeah, that's way better. Okay, great. So let's erase this solve2 function, I guess. No, let's just write solve3. fsolve3, there you go. And to be elves equals a list of I plus 1 and 1 for I in x range of n. So now we've initialized it. And I guess we'll just write this as while true. Let's say I equals 0. We'll write this as while true, and we'll have a breaking condition inside of the loop. I'll let this old version run, just in case that we somehow run into bad times here. While true, loser equals... Oh, wait. We don't need to get to the next elf on our left. That's the whole... That was part 1. Part 1 was getting to the next elf on our left, and we could have done that much more efficiently. But how do we get to an elf halfway around the world from us? That's a little harder, right? Shoot. I thought this was a great idea, and now it seems like it's just as bad as it was a minute ago. So what if... Is there some way we can use the number of presents to figure out how far away our next enemy is? I don't think the answer to that is an obvious yes, because Elf 1 only has 1 present, right? And like, he murders Elf 2, and then Elf 3 has only 1 present, and he murders Elf 4, and so on. And we get up to Elf, like, I don't know, 15 or whatever, and he's still only got 1 present. But the distance between him and the guy that he wants to take all the presents from is smaller than it was for Elf 1, who also had only 1 present, right? So I'm not sure actually how we can make use of that to do anything clever. there we go. We're look at that, like a third of a percent of the way done, guys. Right? Is that right? Hang on, 10? No, more than that, right? Oh man, that's just so sad watching that tick down. So we are, yeah, we're like 12/300ths of the way there. So I mean that's not nothing. Um, but it's not very good either, I gotta say. Hang on, the album I was listening to ran out. Let's try something else. Alright, the chat informs me that I've muted the mic. There must be some keystroke that I have bound to that I somehow accidentally press. Thanks for letting me know. Let's to look at my OBS settings here. Hotkeys. Here's all this stuff I don't know about. Scroll down. Oh! I do have a key bound to mute. And it's one that I actually use, so that explains it. Well, let's clear that for now. What could I put it on that I never use? Apple single quote. Nobody ever types that, right? Not me. Okay, that's exciting. Finally figured out that problem. And why it changes near the beginning of recordings is because I sometimes... I had it bound to Apple M, which is like minimize a window. And I probably did that before like I got the hang of using Mac to minimize windows or something. I was minimizing the audio playing, the music playing window. So, all right, problem solved. I'm going to hopefully stop accidentally muting myself. Here, watch. I'll do it on purpose. Amazing. You guys couldn't even tell, could you? But all right, that's all figured out. So how are we doing now? We're, boy, 2.79. That's like 10%, right? Is it? I guess it's more like... Ugh, not very good. What if we could, in addition to having elves, like, know something, if there was some global counter we could keep track of to, like, have a good guess for how many elves you might need to... I don't know. Yeah, see, I thought I was always muting myself by, like, accidentally pressing, like, clicking on the thing for mute. But I knew that I had not even touched OBS and had become muted somehow, and so I figured it was keywords. So finally figured that out. Hooray. Marvin Beck has solved it. Great. Good for you, jerk. Here's me. Running a very, very slow solution and trying, in the meantime, to think of a fast solution. I've thought of a couple of solutions that are no good, so there's, that's progress of a sort. All right, so, like, could we do anything else with the number of presents that an elf has? Most importantly, it's not even correct that the number of presents an elf has is the distance from him to his leftmost elf, right? Not anymore. It would be if we were murdering the elf to our left, as in problem 1. And so we could have had a faster solution to problem 1, I suppose. But maybe what we can do is not give those presents to the elf who actually, allegedly, in the problem, stole them, but to the elf to the right of the guy who had them stolen. I wonder if skip lists are actually the answer here. Because we kind of have like a linked list that we want to go through, and we want to skip over like a certain number of elements as quickly as possible. And I feel like that's kind of what skip lists are about. let's go on a bit of a Wikipedia adventure. So, Wikipedia skip list. So let's look up what this is. Skip list. A skip list is a data structure that allows fast search within an ordered sequence of elements. Fast search is made possible by maintaining a linked hierarchy of subsequences, with each successive subsequence skipping over fewer elements than the previous one. So it's sort of like a progressively, it's a hierarchical, like, if you're driving somewhere, you can take surface streets, and like if you want to go a little bit further, you kind of head over to the nearest expressway, and if you want to go further than that, you grab a highway or something, that kind of thing. So if you want to go very far, I see. So searching starts in the sparsest subsequence until two consecutive elements have been found, one smaller and one larger than or equal to the element searched for. And then those two elements link to ways back down the hierarchy into less sparse lists. Okay. So everything we want to do is average log n time, right? So it seems like this is actually pretty good. We basically just... Wait, is it though? How do we know what item we're searching for? Because the point of the skip list is that you can say, I'm looking for the elf numbered blah, or at position blah, or something. And we don't really have that property? Day 19 Part 2 strikes again. You are right. God, I hated Day 19 Part 2 last year. I was so mad about that one, I sent Topaz an email, actually, after the whole thing was over. I said it was a terrible problem and shouldn't have been in the thing. So, I don't know. So far, it's... it wasn't because it was too hard. It was because I felt that it told you to find the best solution, which suggests using breadth first search. But if you actually do breadth first search, like, the problem space is just way too large and it never works. And it turned out that, hey, if you use greedy depth first search, like, the first answer you find is always the right one. And I was like, well, but there's no proof that it's the right one. It was incorrect to solve it that way, even if it happened to give the right answer. Whereas today's problem is hard, but I don't think there's any reason that that it shouldn't be a problem. Yeah, so the problem with skip lists is we don't actually know what we're really searching for, do we? It seems like the right idea. To sort of have a fast path to search for stuff on the other side of the list. But we don't know what we're searching for, right? Well, at this point, I'm starting to feel pretty glad that I left a slow algorithm running in that window, because I'm not hopeful that we're ever going to get to it. Yeah, so Eric says Day 19 Part 2 took 4 hours for people to get to gold. But that's not like what I don't care. I was not like trying to get any leaderboard stuff last year. The fact that the problem is hard, like, sure, great, sign me up. Hard problems are fun. I just didn't like last year's thing because the correct solution didn't yield an answer in reasonable time, and an incorrect solution did. Someone in the chat remarks that they're still working on Part 1, computing 1,000 elves every 1.2 seconds. That's going to take a while, all right? Especially if you try to use that for Part 2. Oh, are we still looking at skip lists? I guess we are. I feel like skip lists are the kind of thing that we want, but I can't figure out how to cast our problem in terms of this. Like, how would we do that if we wanted to? We what if we somehow renumbered elves? No. I was thinking, like, what if we renumbered them when elves were deleted? But that's basically what the Dell-based approach is doing, I think. Right, it's sort of renumbering all the elves after the current one every time you delete an elf. But maybe if we could figure out some efficient way to only renumber the right elves. I don't know. So let's actually try just doing by hand a small number of elves here to see something. So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elves, right? Actually, it's probably easier to do it that way. So 0 is going to... let's see, can I... artist mode, please? Sure. So 0 is going to remove this guy. And then it's going to be 1's turn. And there's now 9 elves in the list, right? So he wants to go up by 4. 1, 2, 3, 4. He'll remove this guy. Now it's 2's turn, and he wants to go up by also 4, because there's 8 in the list now, right? 1, 2, 3, 4. So it's definitely not the case, as I did conclude earlier, but I wanted to be sure. It's not the case that we're just eliminating a contiguous subset of elves at the beginning. The fact that the array is shrinking at a rate of n, but we're like sort of moving forward at a rate of n over 2, means that we're leaving gaps. But okay, let's finish this off. 3 sees that there are 7 things in the list, so he wants to go up by 3. 1, 2, 3. 4 now knows that there are 6 things in the array, so he should go up by 3. 7, 0, 1. Now it's 7's turn, and there are 5 things in the array. Go up by 2. He gets 2. Interesting. So we've made a bunch of little sections of deleted elves that are exactly 2 wide each. That's kind of interesting. Oh, you're not looking at this, are you? Sorry. Now you are. I just did by hand the first, 6 elves here. 7 is the one who just took out 2, I think. Or no, we were about to do 7. Yeah, and 7 sees that there's 4 things in the array. He goes up 2, gets rid of 3. 0 sees that there's 3 elves left, so he can only go up by 1. He gets 4. And then 7 gets 0. So we sort of made a bunch of little groups of 2 elves in a row that we're missing. as we went around the circle once. Right? I think that that's what happened. Which would actually be quite useful to know if we could figure out some way to take advantage of that. Does that scale to like an arbitrarily large number of elves? So let's say we put in 16. 0 is going to reach 8 elements over and get number 8. 1 is going to reach 7 elements over and get number 9. 2 is going to reach 7 elements over again, which we think is B, right? 1, 2, 3, 4, 5, 6, 7. 3 sees there's 13, so he reaches over by 6. Yeah, this is going to... Okay. 1, 2, 3, 4, 5, 6. Now it's elf number 4, and there are 12 items, so he goes over by 6 also? Is that right? I guess so. Well, there goes, 1, 2, 3, 4, 5, 6, yeah. Now it's 5's turn, and there are 11, so he only goes over by 5. 1, 2, 3, 4, 5. Right? So we're sort of doing this. Getting rid of 2/3 of the elves in the second half, for a little while anyway. So we've taken out these first 6 elves from 0 to 5 have had a turn. 6 needs to go up by 5. That's 1, 2, 3, 4, 5. 7 sees that there are 9 left, so he goes up 4, which is going to put him here, right? Well, let's actually count it just in case. A, D, 0, 2. Yes. Now, A is a little more interesting. He sees that there's just 8 things in the array, so he goes up by 4. 1, 2, 3, 4. It's the same thing, right? And D is going to eliminate number 5. So in the first cycle around the list, we just created this pattern of gone, gone, present, gone, gone, present, gone, gone, present, all the way across the list. Which is fine. It's a good observation. I'm not sure exactly what to do with it yet, because I don't know where this puts us in terms of, like, for an arbitrary number n, how do we know which elves will remain? Like, when oh, interesting. So, sorry, bumped the laptop there. I forget whose turn it was here now. Is it Zero's turn next? I think so. Because A... Yeah. Wow, did I just type a bunch of dots on the screen somehow? I don't even know how I could possibly have done that. So I think that we can sort of, if we think about it enough, by the way, the slow solution is 1/3 of the way done. Actually, probably like 2/3, because each iteration is getting faster. So there's that. So it seems like we can observe that this pattern is going to occur in the list. And basically reduce the initial input to be one with 1/3 as many items if we can figure out exactly where the cursor should end up when we're done, right? Was it a coincidence that, well, so first of all, it's not perfect because the cursor is on 0, and like 6 and 7 are the ones, like they're two adjacent non-removed elves. So we don't have the perfect present removed, removed, present removed, removed forever. But it seems like there's a lot of regularity to the process here, right? If we could figure out a closed form solution for like what happens to the cycle, what happens to the circle after one iteration, we could remove that one iteration from consideration. And then just sort of renumber all the existing all the elves that exist, and do that again. Right? If we have a solution that given an input and an offset, so given an input array and a starting offset within that array, if we can produce a smaller array with a smaller array of elves and a new pointer position without having to do really expensive operations, if we can do that relatively cheaply, then we can just sort of apply that process iteratively. And the trick is actually doing that. Because as you see here, I guess it's because our input is not divisible by 3 that we didn't get a regular pattern. Of course it couldn't be regular because the pattern is three elves wide. So it can't fit regularly into an array that is 16 bits wide. What are the prime factors of our puzzle input? Hello, I can't. Can I just like type that into Google? Prime factors of this number. Any luck? Find the prime factors of a number. All right, well. Enter a number with a maximum of 9 digits. Ha! There's only 7 in this. It's prime. All right. Well, that's interesting to note. Yeah, my computer, by the way, you guys are talking about how fast your slow solutions are running. Mine is running even... So, I mean, it's like just a MacBook that's several years old. But it runs real slow when I'm recording as well. We can open up the activity monitor here. You guys can't see it, but I can. And OBS here is taking up... Hello? Where is even OBS on this list? There it is. It's taking up like 2 CPUs, and I don't know how many CPUs this machine has, but it's not very many. And Python can only take up a maximum of 1 CPU, but my experience has been that, yeah, right now Python is getting like half of a CPU. So it could be running twice as fast if I weren't recording for you good people. But you know, we all make sacrifices for our art. So anyway, what I'm getting at is that I think there's got to be a solution we can write that takes advantage of this regularity. And I bet that the spot where this happens is something to do with, like, our prime mod 3 or something crazy like that, right? It's somehow related to the number 3. But I don't know how exactly. Maybe it's the prime divided by 3 modulo the prime? Because you like... Yeah, that's probably what it is, right? So what is... 16 divided by 3 is obviously not a real thing. But there is some number that you can multiply by 3 and get 16 modulo... and get... well, actually, we don't want to divide by... Do we? Is it like 8 or something? 6 or 7? I don't know. Somewhere in here. I'm sure it's something to do with modulos and division, but I don't know the answer. Yeah, so I mean, as Topaz is saying in the chat, it is possible to write an efficient solution. And I feel like I'm on the right track with thinking about it in terms of this regular elimination pattern here. We can basically, like, things start to get messy once a... Once, so we just had, like, D was the last one to take a turn, right? And so now it's Zero's turn again. So what would Zero do exactly? He would see that there are 6 things left in the array? Yeah, 6, and go up by 3. 1, 2, 3. Get here. I don't know. That seems okay. So we would put an X here, and that's this guy's turn. And he would go up by only 2, right? I'm having trouble counting how many things are in the array now, but it's 5, so he would go up by 2 over to A. Remove that. This guy also goes up by 2, which brings him back around to 0. Now we go up by just 1 from D, which gets us to 3, and 1 from 6, which gets us to D. So, so in this, like, with 16 elves, it seems like number 6 wins. Let's confirm that real quick. Solve 2 of 16. It's 4. Oh, man. Don't be wrong. I hope I did it wrong by hand. It would be quite sad to have an incorrect solve algorithm here that we've been running for like 45 minutes. But maybe what we could do is, okay, so we start at 0, okay? And we only remove things from the list until we would get some wraparound. We can do that quite efficiently by just removing every other elf starting at some position, right? So 0 goes up by 8, removes 8. 2 removes 9. 3 removes B. 4 removes C. And then 4 removes E, and 5 removes F. Right? So this is sort of an interesting thing we could do. We could try... wait, have I removed 6 of them? Is that right? I guess so. 0 removed 8. 1 removed 9. 2 got B. 3... Yeah, okay. Alright, 0 through 5 have all acted. So, in this way, we've sort of, in one go, removed 1/6? No, 1/3 of all the elves in the array, right? And that was done pretty simply. We could do this mechanically, I think, by just sort of, for each, we basically take the number of elves there are divided by 3, and let's say round down? Up? Up, I guess. Because we had 16, divided by 3 is 5? Point a bit. We rounded up and that was okay. But if there were 17, then the next one removed would have been like 0 or something, wouldn't it? But it's sort of a relatively efficient process for removing 1/3 of the elves. And then we could throw away the whole list that we had and renumber them, so that these first elves are still numbered 0 through 7, but we take this one that was labeled A, and we label it, and we put an A into the list at position 8, and that's when we do the compaction. So we don't have to keep compacting the array every time we delete an elf, only when we delete 1/3 of the elves. Yeah, there's people in the chat discussing approaches to solve this faster, and I'd rather not get a lot of hints. Somebody suggested even just print out the solutions for like 100 elves and 200 elves and 300 elves and like see if there's a pattern. But I feel like there wouldn't be a very interesting pattern because like it'll have weird modulos involved or something that are not so obvious to the human eye. But I feel like there's real promise in this approach if we can just figure out exactly how many elves we can comfortably remove. Right? So here we were able to use the first 6. All right, let's actually, we can do this for a small number of elves relatively comfortably. So let's try like 0, 1, 2, 3, 4. Really? Control O puts a line there? That surprises me. Artist mode is kind of weird. Don't use artist mode, kids. So here there's 5 elves, and if we were to take the first third of them rounded up, that would be 0 and 1. So 0 would go up by 2. He'd remove this guy. And then 1 would also go up by 2 and remove this guy. Oh! This whole, like, 2x's pattern, it doesn't even hold for things with different, does it? I guess not. How long have we been streaming here, guys? It's a long episode, I tell you. Okay, so what if we, like, try a relative... I feel like for any number that's large enough, this 2x's pattern appears. It has to, right? But, let's try, like, 10. 10 is even. That's interesting, I guess. I can't even type 6, 7, 8, 9. 0 goes up by 5. 1 goes up by just 4. 2 goes up also by 4, right? 1, 2, 3. 1, 2, 3, 4. Yeah, so that's the same pattern. As we would sort of expect, because we took 16 and we subtracted a multiple of 3 from it. We get something that looks like this. Now, what if we shrank it a little bit from 10 to, let's say, 9? 0, 1, 2, 3, 4, 5, 6, 7, 8, and then just 8, right? So 0 goes up by 4 to here, and 1 also goes up by 4 to here, but then we start with the regular pattern, right? 2 goes up by just 3. 3 also goes up by 3, bringing him back to here. So it seems like if we, yeah, ugh. It's kind of hard exactly to know. And I bet if we took like 8, there'd be a wider space before these x's start showing up, or maybe a narrower space or something. We kind of have like this pattern of keep remove of like dot dot dash dot dot dash dot dot dash, right? Sort of. That appears about halfway through the array, but what part of that pattern you start at varies with like your size of the array mod 3. So I feel like we could use that to make some progress. Oh, someone is asking, how did I solve part 1? I used a queue. Which, I mean, you might say is a linked list, but it's not. I mean, it's probably implemented with a linked list, but we're using it as a queue. What are y'all's inputs? Somebody asks. They want to try out a very simple solution on an input. Well, tell you what, here you go. You can have mine if you want. I'll paste it into the chat for you. But don't tell me the answer, of course. Yeah, we can even go, since we don't have any clever ideas, we can review my part 1 solution here. I basically just created a queue and pulled the first 2 items off the list, the front of the queue, and then added the first one back to the end, and kept going until we ran out of else. Not the most efficient thing in the world. I think it took like 30 seconds or something, but it works. Basically, the idea is there's just each, when it's time for an elf to remove another elf, it's going to be the elf who's after him in line, right? So you can just take both of them off the list and then put the first one back at the end, and he'll wait his turn. Yeah, so the thing, Josephus Circle, someone mentions. Is that the, like, famous problem that this is? I know it's, like, a famous thing that I've heard before, and that there's an easy solution for at least part 1. Someone made a circular linked list and just sort of deleted things from it. Sure, that seems fine. I'm kind of disappointed with how much difficulty I'm having with this. I don't know that there's really anything exciting to say on air. I don't really feel excited about going and implementing the version that efficiently removes a third of the elves, because, like, there's these boundary cases and there's some awkward bookkeeping. I don't know, it just doesn't seem like that much fun. And of course, having a slow version running in the background certainly makes it less compelling to figure out a fast version. So all right, maybe we can think some more about how we might implement this more efficient version. We would basically take the first half of the elves, like those are first half rounded down of the elves, and just copy them verbatim into the next version. Right? That seems safe enough. And then, for the elves above that, figure out whether they should be included or not, based on their... Well, actually, I guess you might rather say, figure out what number mod 3 is the correct one for the elves that survive this pass of the culling. I guess the other thing is then that we have to figure out what the pointer should be for the next step. And we renumber them so that the one at the pointer is first, I guess. Ugh. That's not so easy, is it? Blah. Yeah, I don't know. I'm kind of feeling like it's probably a good time to be done with the stream, because I'm just kind of feeling a little bit dead-ended, and, like, there's an approach that seems like it's good, but I can't figure out how to do it, and, like, it's harder a bit to think when I'm streaming as well. Although, to be honest, probably what I'll do is just let it run overnight on the slow version and, like, let that be the answer. I'm not too concerned about leaderboarding. Yeah, I don't really want to figure out the boundary conditions of this other approach. Apparently there's, like, some really fast thing you can do that's probably faster than this, according to, what's his name, Marvin Beck, who claims he has something very fast that I guess is probably just a formula or something. But this is going to make pretty bad YouTube footage already. And if I just sit here staring at it for longer, stuck on, like, how to do the more efficient thing, it's just going to get worse. So, I don't know. We had fun with the first half. The second half was kind of fun, but frustrating. And and I'm not really going to stick around with it, I think. So I guess that's the end of the stream, and the video if you're watching this from the archives. Yeah, well, of course the leaderboard is capped. Like I said, I don't care that much. Have I really only been live for 52 minutes? That doesn't seem right. OBS says it's been longer than that. Huh. Interesting. OBS says I've been streaming for an hour and a half, and YouTube says I've been streaming for 52 minutes. I see that it's actually been an hour and a half, so I guess it's time to report a bug with YouTube? I don't know. Anyway, as I said, it was a very long, drawn-out goodbye. Thanks, everyone, for watching. Hope you enjoyed as far as we did get, and I'll see you next time.